Hi everyone, I hope I'm in my groove again. I've been having a tough day trying to shoot these videos, so I'm going to make them separate. So this is our practice exam fall 2015, and I'm kind of going slow through these questions so I can treat it like a test review and kind of help you with some of the concepts and maybe help you with your cheat sheet a little bit. So let's tackle number 7, number 8, and maybe even number 9, all in the same video. They're all mechanisms. The first video was a mechanism, so I'm kind of staying with the theme, and then we'll do some synthesis together. So let's tackle this first one. I'm pretty excited for this one. It's a really fun question. So let's go through our process. We just did our process on the last video. First things first, we have to figure out, remember we've got 5 reaction types. So we need to figure out which one we have. Do we have radical halogenation? Do we have the SNs? Or do we have the Es? Remember, they all have their own set of rules. So you want to approach this test by figuring out what in the Sam heck. There's an easy way to answer this one and a hard way. Let's do the hard way first. It is a test review, and that makes me happy to do it the hard way. So first things first, let's go through our same process. Let's find our leaving group. Look at that. That is awesome. And then, oh, holy crap, we don't actually know what the product is. So that makes it a little bit trickier, but I think it's safe to say if you already have your bromine, that this is probably not a radical halogenation because your bromine's already there. And then let's look at our electrophile. That is right there. That is nice and secondary. Okay, awesome. Secondaries can do everything, so that's perfect. Okay, so that doesn't help us. Now let's take a look at our reaction conditions. We've got sodium methoxide and methanol. Ooh, okay, you got 2 things. So right away, it's not the ones, right? We learned in the last video that the ones have solvent nucleophile. They're the same thing. So this is either an SN2 or an E2, and how would we normally tell those apart? We'd look at the product, and it would be pretty easy to tell. For this one, we can't tell from the product. We have to predict the product. So how do we tell SN2 versus E2? Well, on a secondary electrophile, how do you tell? You have to look and see if you have a nucleophile or a base. So this is something you want on your cheat sheet. You definitely want to be able to tell those 2 apart. And this feels like a sparkle pen moment. This is a base, not a nucleophile. So this is on a secondary, that's a base. So base means we cross out the SN2 and we have an E2. Okay, now there's a much easier way to go through this process, and that would be to actually just read the question because it says right in there elimination. I'm sorry, I just made my daughter laugh at that one. All right, so let's go back. Now that we know that we have an E2 and we know our conditions, we have a whole set of rules that are my favorite for an E2. The first one, you have to find your beta hydrogens. That's what we're looking for. So our beta hydrogens, let's do a little color coding and highlighting. Those are next door, so that's there and there. We definitely have beta hydrogens. Okay, and then the next thing we look for is our size matters. Our base, that size matters. So let's take a second. Let's write a quick note. Sodium methoxide, is that small or is that large? That is small. So that matters. That's going to tell us we're going to make that innermost alkene. We're going to follow Zetsef's rule on that. And then number 3 is my personal favorite, and that is anti-periplanar. These reactions have to happen anti-periplanar. So if we are going to happen anti-periplanar, we have to know what these molecules look like in space. So that means either Newman projection or chair. What? Hello, Unit 1. We are right back to Unit 1. So I can tell right away from the fact that this is a nice cyclohexane that we are in the, I just said nice and then I drew crappy. Let's try that again. Okay, nice cyclohexane. So that means that we are going to be drawing some chairs. We have got to figure out our antiperiplanar. So I'm going to be bold and not even read the question yet. I'm just going to go right ahead and draw the chair for this one. So our bromine, I'm going to put it up here. It's nice and bold. I'm going to put that axial. So then both of these methyl groups, they are bold also. So that means they would actually have to be equatorial, leaving hydrogens as axial. And then we've got an isopropyl that is bold also. So what does bold mean on this chair? That is going to be up there. Okay, so where do we go from here? Well, if we're doing an elimination reaction on this, we have to find antiperiplanar. When you're in a chair, how do you know antiperiplanar? It's actually awesome. It is very specific. You need axial, axial. That's it. You need your leaving group and your beta hydrogen, axial, axial. So here's our leaving group. Here is our beta hydrogen and our beta hydrogen. Well, in this case, shoot, they are both beta hydrogens and our leaving group, our axial, axial. So what is our product? Well, it's a mixture of both of them. Wait for it, you gotta write both. Okay, so we can go to this side and this side. Are they different? Yes, we have stereo centers there. Okay, perfect. So hang on a second. Trick question. Why is this not bold? Because our alkenes are sp2, they are not sp3. Do not put a bold there or I'm taking points off. And they are flat. sp2 is flat. sp3 is trigonal planar. Okay, so now we've got our substrates. Awesome, we just predicted our product. So I'm gonna do the same thing for the bottom one. Let's go ahead and draw another chair. Got our leaving group. Oh, hang on a second. We've got the exact same configuration with those methyls right where our beta hydrogens are. So there's no change there. Well, that just screams trick question coming. I mean, they're the same. All right, well, this is different. But is that where we're doing our reaction? No. So here's our isopropyl. All right, do we still have, here's our leaving group. Do we have axial, axial? Yeah, and we have it in both. So we need to draw both products. I need to give myself some space here. Let's draw both products. Shoot. Okay, and this one. Okay, we have both of them. Well, now what in the Sam heck could the question be? I guess it helps to read the question before, but why, you know? All right, so we just drew the chair configuration, and now here's the fun part. I almost feel like I need another highlighter in a fun color. Let's go purple. Okay, so let's look at this. Which one will be faster? Please explain. Well, we're making darn near the same products, except would one of them be faster than the other? Hold your seats. This is a sparkle pen moment. Hang on. Let's go all the way back to Unit 1. Unit 1. Let's put a little sunshine around that. Out of these two chairs, which one is the best and which one is the worst? And why do we care? This is our best chair. This is our worst chair. So why do we care? Because our best chair is going to actually sit in that configuration. And that is where we have axial interactions. In our worst chair, are we actually going to look like that? Heck no. Less than 1% of the time that structure is going to actually look at that. what's it actually going to look like? It's going to look like the flip. The chair flick no longer has axial. So between the two of these, which one is going to be the faster one? It's going to be this top one. Let's put some sparkle pen in there. This one will be the fast one. Okay. Awesome. All right, let's scroll down. Let's do the next one. Oh, this is going to be fun. Okay, let's go through our process. We've got a nice process. Let's figure out what kind of reaction this is. We've got, hang on, what do we have here? We have, okay, what do we have here? Sorry, a little distraction there. Got a phone call. Okay, so let's look at it. What do we have here? We've got, let's find our leaving group right here, chlorine. Okay, done. We found our leaving group. Let's figure out which kind of reaction this is. Is it an SN? Is it an E? Okay. We've got our leaving group. Our leaving group tells us our electrophile. Our electrophile is right there. Our electrophile is secondary. Oh, son of a, right? That's a kick in the chops. Secondary means we can do any of our reactions, and we have chaos with each one. So of course, this is my favorite question. Okay, then what is our substrate? Our reagent. We only have one. We only have a solvent. So that means that our solvent is our nucleophile. Okay, so what is this a recipe for? Well, we didn't add a halogen, so it's not a radical halogenation. Did we substitute anything? Does OMe end up anywhere in our product? No, but we formed a double bond, so that means we cross out the S's and we keep the E's. Now we have to figure out, is it an E1 or an E2? And how do we distinguish between the two of them? E2 has a nice negative, strong base, and an E1 is nice and neutral, something with lone pair. So this is definitely an E1. Okay, E1s are awesome, especially secondary, because they rearrange. All right, so let's see if we can figure out what happened here. So now that we know our type of reaction, we already know our first step. No matter what, whether you see your product formed or not, you already know your first step. Your leaving group has to leave. And then if our leaving group leaves, what does that make? Okay. All right, well, it leaves a naked carbon, that's for sure. We got a nice carbocation right there. And that carbocation, remember, we pause here. We pause. Is this secondary or tertiary? This is a secondary. That means we're probably going to rearrange. We're going to rearrange to something better. And what would better be? Something tertiary. Okay, so now you kind of let your product guide you, but you also know in your heart that I'm trying to trick you. So let's go ahead and identify all of our things that can move. Remember, we can move a bond to carbon, or we can, boy, that came out crappy. We can move a bond to carbon, or we can move a bond to hydrogen, but only if they're next door. So let's go ahead and mark what we're looking for. Okay, next door right here, we've got a bond to carbon, and we've got bonds to hydrogen. And then next door on this side, we've got bonds to carbon and no bond to hydrogen. So we generally have 6 options every time we have a carbocation rearrangement. Now, some of them might be the same. So what your gut is telling you is, well, let's start with one of these hydrogens and let's move it and let's see what happens. So let's just try it. Let's just move one of our hydrogens. So if my carbocation is here and I'm going to move this hydrogen, you know I like to color code. Let's fill in that space. All right, we now have our hydrogen here. Oh, what happened? Okay, we now have our hydrogen here. And our carbocation here. Okay, now that's kind of appealing, right? Except, where would our double bond end up? And is that in the right place? No. Ooh, so that seemed like the favorite. That would be the one that you'd want to move. And then you would think, well, can't I just move that methyl? And then you start moving 6 ways to Sunday. And really, that's just not the right bond to move. So now let's try and move something else. What happens if we move this bond? The one right here. Okay, let's try it. It's going to get a little real in here. It's going to look funny. We've got this carbocation. We've got electrons right there. What if they move over and fill in that space? Now, you know I like to draw these funny, and then I'll draw it pretty. So let's just keep this side of our molecule the same. Let's keep this side the same. And then let's draw our new bond. And then let's figure out where our carbocation is. Right there. Huh. Okay, well, remember our rule. We have to make something better. So right here, we made another secondary, not better. Right here, we just made a primary, way not better. That's not going to happen. So it looks like we're going to need to focus on this side of the molecule. And let's move some of these bonds. So let me try the obvious one. Let's move this methyl real quick and let's see what we end up with. Okay, this is where we start, except not such a fluffy line. Okay, let's start right there. All right, let's move this one. Let's draw halfway decent. Y'all, I think I need some coffee. Let's draw halfway decent. So we just moved this here. Okay, where does that leave our carbocation? Here. Oh, this is tertiary. Now we're getting somewhere. Except where would our double bond end up for this one? It would end up here. Is that our product? Nope. Nope. All right, take a screenshot for a second or pause because I need to erase this and let's move something else. Let's just try it. Maybe I ought to sip some coffee. At least my handwriting's getting slightly better. Slightly. I'm getting used to writing on this iPad. All right, let's give ourselves some space and let's move some more bonds. And let's try it again. Okay, let's draw this. Okay, now we've already moved here, here, and here. And we moved here, and those didn't work. So let's try this one. Let's try this one. Okay, so let's take the electrons in this bond and let's move them over. Okay. Now again, I'm going to draw it funny. Okay, let's keep what we know. Okay, Let's keep this. And then let's figure out what just went where. Let me draw this just a little bit prettier down here. We had this and we had this. Okay, now what we just moved was this bond went from this carbon to this carbon. So let's move it. These two were still attached. And then where does our carbon, carbocation, end up? Well, we really violated the carbon right there. Ooh, let's draw this pretty. All right, we went now to a 5-membered ring on that side and a 6-membered ring on that side. So this bond was our pink. This was our carbocation. Oh. Okay, now where would our double bond go for this one? Where could we have our double bond? Well, our double bond now can end up right there. Okay, so let's draw the mechanism to that real quick. Let's just do a quick review. Something is going to take that beta hydrogen and fill in that double bond. And then what does our product end up looking like? Like that. Oh my gosh, aren't these the same thing? Yeah. Okay, that's a sparkle pen moment. I love it. That makes me super happy. Okay, how do you make organic hard? You draw it funny, y'all. You know that. So all that is this. These are the same. They are just flipped. Okay, wasn't that fun? Carbocations are nice. They're super fun. Don't be afraid to take out your scratch paper. Just start moving bonds. And remember, I'll always follow the rules. I only move carbon and hydrogen. I only move from next door, and I don't do more than one rearrangement. So if you found yourself rearranging 6 ways to Sunday, just stop. Something was tricky in there. That's not how I would approach that problem. Okay, awesome. So let's scroll down one. Let's see what this next one is. Let's see if we can tackle this one, and then we'll stop this video for a second. Okay, let's do our same process. Start with your 5 reactions. You know what they are. You got your SNs. You got your E's. Let's figure out which one is which. Here's our leaving group. Here's our electrophile. Okay, what kind of electrophile is it? Tertiary. And, let's take a look at here. We've got 2 things. What are they? Well, back in 2015, I used to use a couple different bases. I'm going to help you with this one. Tert butoxide is a base, and it is a large base. Now, we kept ours to LDA, so you might have the same problem on your homework and your exam. We would just use LDA. A little bit more modern. Both bases are used. We've got both bases in the lab. So, of course, you make your LDA. You don't buy it because that'd be a waste of money. But we've got both in the lab. So this is a large base. All right, so let's see. And we have formed a double bond. So right away, not radical. It is not a substitution. It's one of the E's. And because we have a nice negative on our base and we have 2 things here, this is not an E1. This is an E2. Okay, but this is the fun part. So this is an E2 with a large base. So what hydrogen are we taking? Because we've got beta here, here, and here. We have 3 sets of beta hydrogen, but your large base is going to tell you which one to take. Take the easy one. We take the easiest to get to. We take the least hindered. Okay, so what is our mechanism then? Well, let's redraw this substrate. Let's draw the E2 mechanism. Let's just draw Do we care about the stereocenters? Well, kind of. Okay, here is our leaving group. Here is our easiest to get to beta hydrogen. So what does our mechanism look like? We're going to take that huge base with nice available electrons. You got a nice pair of electrons right there. Let's put the 2 in E2. We need a collision. This happens all at once. You take this hydrogen. These electrons go right here. They collapse down. They make a double bond, and they push off your leaving group. So that's your mechanism. We just made the product. Let's redraw it. We just made this double bond. And then what's left over? Well, the beauty of matching base and solvent is that you just made your solvent. And you just did that. Okay. Awesome. All right, let's stop this video here. We just did 3 of these test questions, and then I'll start another video and I'll do a couple more